Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
Welcome to Roots, Radicals, and Rational Exponents. Before we get started, I want to make sure we understand what a root is, what a radical is, and how that relates with what some of us know from doing some computation. So for example, 3 to the 4th power is 81. Okay, so the 4 there is what's known as a power. A lot of times in math, not only do we have to go forward, we have to go backward. So therefore, 3 will equal the 4th root of 81. Okay, now, this part right here, this symbol, a lot of people call it the square root symbol. It is not just a square root symbol. It is known as a radical. The 4, the tiny number there in the radical, is the index. When the index is 2, we just don't write it, and that's when the square root comes in. And then the number underneath is called a radicand. And for computation reasons, the radicand must be an integer, and that is to make computations something that we can work with. Prior to calculators being widespread, we had to utilize charts that were approximated using complicated calculus and other types of mathematical skills so that those who didn't know that kind of math could go ahead and continue with whatever they were working on. So that's one of the reasons the radicand must be an integer. Again, integers are not fractions, they're not decimals. So whenever you're finishing any problem, you always reduce to the lowest terms. That means your radicand must be an integer, not a decimal, not a fraction. And so we'll have to focus on ways to fix that. I utilize some different types of ways to reduce radicals than a lot of textbooks, but I find that it works really well. So again, prior to calculators, if you came across a problem and you wanted to utilize this numerical value, its decimal approximation in a problem, you're not necessarily going to find it in the charts because the charts did as little as possible. Because if they put in every single root of every single number, it's just not physically possible. So they went ahead and they reduced these radicals. So the way most mathematicians are going to teach you how to do this is that we know 27 is 9 times 3. And I've changed these both to a square root. Again, it's a square root because the index is assumed to be a 2. They just don't write it there. And most of us know that the square root of 9 is 3. And then, so they'll just change this to 3 times the square root of 3. Now, 3 is a prime number, so this radicand would be in the charts that they have because the charts normally utilize prime numbers. Again, that's what this would look like in a normal textbook. However, I don't like doing it that way. If you've seen some of my other videos, I talk about folding socks. So I have 27 and I change it to, the prime factor is 27, which is 3 times 3 times 3. Since the index is 2, I circle pairs, and when I fold socks, I fold them together, roll them in a ball, and put them away. And I think of the radical symbol as a basket, and sometimes the dryer eats socks, so this 3 here is still solo. And the reason I do folding socks is we can have, socks for your dog, or maybe you want to put socks on a spider. I don't know what that would look like, but hypothetically speaking, I utilize those kind of imageries to help us out. I have a friend with a 3-legged dog, so maybe she wants to put, socks on her 3-legged dog so that he doesn't burn his feet on the pavement. A couple of things to remember is that even index When you have an even index, your radicand must be greater than 0. And this is because negative 2 to the 4th is positive 16, and 2 to the 4th is also positive 16. So when I go to do the 4th root of 16, that's possible. I can get 2 or negative 2. And I'm just saying that. Normally we only do the plus or minus in equations, but the 4th root of negative 16 is undefined. And that's because anything to the 4th power is positive. Notice I said this is undefined. The only time that I've worked with imaginary numbers is for square roots. So we're not worrying about imaginary numbers with other indexes other than the square root symbol or an index of 2. Past that, I've done a lot of math and I have not done anything with a 4th root of a negative. I've just left it as undefined. However, what about odd indices? Okay, well, negative 3 to the 3rd power is 27, is negative 27, sorry. And positive 3 to the 3rd power is positive 27. So here, with an odd power, we can get a negative number or a positive number, depending on what we started with. So we can do any radical with a negative index, or sorry, with an odd index. So with an odd index, the radicand can be any integer. Okay, so keep that in mind. And again, only integers are allowed in your final answer as a radicand. Okay, so we're going to practice folding socks. And again, I prefer folding socks just because it gives one method, and for those who may not have super strong memorization of different powers. So the radical is 75. Now, for those of you who want the Brooke format, I know 75 is 25 times 3. And if I do the square root of 25, I get 5, and 3 is a prime number. I know that. For everyone else, we know that it divides by 5 because it ends in a 5, and that's 5 and 15. And 5 and 15 is 3 times 5. So we're doing 3 times 5 times 5. There's no number out here, so the index is assumed to be 2. So we're folding pairs of socks. Fold them together, roll them in a ball, put them away. And what's left in the radical is, or what's left in your laundry basket, is a 3. So both methods work. I will show you why I'm using folding socks here in a moment. Okay, so now we're going to do the 4th root of 32. Again, they want us to have the smallest integer possible underneath, just to keep it in tradition with how it was done pre-calculator. And I don't know about you, but do you know your powers of 4 to be able to reduce this? Okay, so most people are going to say, well, 32 is 4 times 8. 4 is 2 times 2. 8 is 4 times 2, which is 2 times 2. So there's 1, 2, 3, 4, 5 2's. One, 2, 3, 4, 5. Ooh, let's refocus, come on. All right, so because the index is 4, we're folding socks for our 4-legged friend, Fido, whatever. Okay, might be a cat, might be a dog, I don't know, your 4-legged friend. So we have to take 4 of a kind, roll them together in a ball and put them away. Whoops, I had 4 on the brain. 2, we had a group of 2's. we were folding in groups of 4. That's why our index is 4. And it's a little number. That leaves us with a 2 inside the basket. Now, if you're trying to check this in a calculator, especially if you're using a basic calculator, make sure you use this button. So you'd want to do 2 times. And if it's like a basic TI 32 scientific, not graphing, you'd have to do 2 times, use that multiply sign. Then you could write the index and then that number, parenthesis, 2, close your parenthesis. So this is how you would type it into a calculator to check it compared to this. Here we would write 4x. That's a button on a calculator, and then 32. So if you're trying to verify, this is how you would be typing it. Okay, so I use the folding socks method. A book is going to say, okay, we had 5 2s, right? Okay, so I'm going to split them into 4 and 1. And then the 4th root cancels out the 4th power. It's a little more how a book would do it. I just like folding socks. I've just worked with a lot of students and it's worked over the years. So now let's do it. All right, the third root is 648. So this time, unfortunately, we have a 3-legged furry friend. A friend of mine has one, and it had an injury trying to get out of a kennel before she adopted it. And so that's how he came to her. It happens. So I understand. I care about the animals, but it just was an example for a visualization. So let's do the prime factorization here. It happens to divide by 8 because 64 and 8 both divide by 8. So 8 and 81. 8 we know is 4 times 2, which is 2 times 2. 81 is 9 times 9. So 3 times 3 and 3 times 3. We have 1, 2, 3 2s, 1, 2, 3, 4 3s. Third root of 1, 2, 3 2s, 1, 2, 3, 4 3s. All right, so we're folding socks for our 3-legged friend. We have a group of socks here, a group of socks here. We're going to fold those together, put the 2 away, put the 3 away, and we still have a 3 as a radicand. Will the number here always match the number there? No, it just happened to be what it was this time. So 2 times 3 is 6 third roots of 3. I will be doing videos in the future that talk about numbers where we don't have an integer underneath a radical, but that's not the point of this video right now. I'm going to make a whole video just based off of that. I do want to go ahead in this video and help us go from radical form to rational exponent form. So if you notice here, I don't have enough of the x's to make a full group of 3. I'm missing one. I only have 2/3 of my group. So I'm missing some socks, so this is reduced. However, I can say this is the same as x to the 2/3 power. I don't have a full group, I just have 2/3 of a group. So if you'll notice, the power inside became the numerator and this became the denominator. I will tell you that this is also equivalent to all 3 of these mean the exact same thing. I could square the value and then do the 3rd root of it. I could do the 3rd root of it and then square it. Or I could just say, hey, it's x to the 2/3 power. And the different formats can help me at different times. So just making sure that we understand that those are all the same. And this can actually help us shortcut our folding socks. For example, we had the 4th root of 32. And we rewrote that as 4 and we had 5 2s. So do you see how we have 1 and so if I rewrote that using exponents, that would be 5 fourths. Or 1 1/4. I don't really like writing it 1 1/4, but think of it, our answer was 2 with 1, 2, see, one group with 1 out of 4 left over. So there's our 1 1/4 coming out. And of course, the 1s are assumed. So if that helps you as well, we can think of it that way. So index of 4, x to the 20th. We could write 20 x's down and then circle our groups of 4. Or we could think, how many groups of 4 are there in 20? Well, I'm betting in your brain you just took 20 and divided it by 4 and got 5. And that is absolutely correct. Now, there is a small little bitty catch because this was an even index. You need absolute value signs around that variable to keep it real. That way we're saying, hey, you got to make sure you use the positive value of x to the 5th, not a negative value of x to the 5th. You've got to have the positive value. That way you do not have domain errors. If this were odd, it wouldn't matter. But because this is even for an index, it causes us to put the absolute value signs. Let's say we're doing the 6th root of y to the 24th. We get y to the 4th. Now, in this case, I don't have to put on the absolute value signs, but it's not wrong if I do put on the absolute value signs. Why is that? Well, anything to an even power is already positive, so including the absolute value signs is a little bit redundant. In my classroom, I'm not going to take off for that, but you might see it in the books where it's only when this is even and the power is odd that you see the absolute values. Even doesn't matter. And if it's an odd index, it doesn't matter. You only must do it if you have an even index with an odd power on your variable. That's when you have to have it. So please keep it in mind. It's just to make sure that it stays as a real answer. Not a big deal, but all right. So let's do the 3rd root of x to the 22nd. Now, we do not need absolute values because this is an odd index, so it's not going to matter. So if I rewrite it just using rational exponents, I get x to the 22 over 3. If you wanted it back in radical form, there's a full 7 groups with 1 x remaining. Okay, so use these to your advantage. C to the power of a over b is equal to b, c to the a, which is equal to all those are the same equivalency. You can use them to an advantage. Okay, now reminder, if b is even and a is odd, use the absolute value. Okay, that's only if b is even and a is odd. So again, use it to your advantage, and just as you're simplifying, either use the exponent rules as a traditional textbook would give you, which I kind of showed you, or use the folding socks. Folding socks is a great visualization tool. What the book is going to do is anytime you have b root a to the b, because these cancel out, it will equal a. because they're just doing, well, b over b reduces to a. And that's how they're going to traditionally reduce radicals.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Then drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.